Hello, folks. This video is going to cover sampling distributions of proportions and their properties. And I'm going to kind of jump into the formulas and I'll explain where all of these formulas came from. And then the next video after this, the last one in this section, will show you um, some practice problems and like how to actually solve problems with sampling distributions of proportions. All right, so let's go ahead and jump right in here. Okay, so I'm hoping that you watched the first two videos in this section to get a general idea of what a sampling distribution is. Okay, this section mostly focuses in on proportions. Okay, so what sampling distributions of proportions do, okay, is they show us how well the sample proportions, which uh, sample proportions, remember, are p hat, right? I'm leaving myself some space so I can write the actual symbol out for you. Okay, so it shows us how well the sample proportions estimate the true proportion, which, remember, is represented just with a lowercase p. Okay. One sec, let's go right here. So remember, sample proportions are represented with a little p hat. Okay. Remember, the goal of using a sampling distribution is to essentially garner or figure out what the true values are if you don't know them, right? Or it's like a representation of how good your sampling method is, essentially, right? And how well the different proportions that you get from your samples will actually give you like the true value, right? The true proportion, right? So, good thing to remember, right? Whenever you think proportions, you want to think categorical variable. Okay, so and it goes both ways, right? Categorical variables, typically you're dealing with proportions. Okay, so hold on, guys. The equation thing's not going to work very well for me, so I'm going to have to just write this out for you. Okay, so just as a quick like reminder for you that p hat, okay, a sample proportion, is just the count of successes in a sample. I could spell, that would be awesome. Okay, divided by the size of the sample. Throw that line in. Okay, which is basically, okay, which is basically capital X, right? Remember, if you remember from population distributions, right? X is your variable that you're looking at, right? So successes divided by the size of the sample, which is n. Okay, and the reason I'm bringing this up is because I want to show you where the formulas for mean and standard deviation of a sampling distribution come from, because they can look a little bit intimidating if you're not sure where they come from, right? Okay, so I want to have you flash back for a second and remember our values for binomial variables. Okay, so if you think back to Unit 5 when we learned about binomial variables, right? If we have a binomial variable x, the way we would find the mean of that variable is we would do n times p, okay? And the way we would find the standard deviation of that variable, we would do the square root of np, right? Parentheses 1 minus p, okay? If we take the mean and standard deviation for a binomial variable and divide those formulas by n, okay, in order to convert x into p hat, right? So we're taking x, dividing by n to get p hat. What we end up with is what you see on the on the left side of your screen, but I am going to write out for you here on the right-hand side. Okay, so if we want the mean of p hat, right, we would do np divided by n. The n's cancel each other out, so you're just left with p, which is the true population proportion. Okay, and then standard deviation is a little bit more complex, right? So this is 1 over n times square root np 1 minus p. Okay, I need to bring this n, the one on the outside of the radical, inside the radical. So in order to do that, I'm going to square it and move it inside the radical. So I'm going to write this way. So we have np 1 minus p divided by n squared. So then you have one of those n's that cancels out. Right, so you have the squared that cancels out with this n. So the formula that you end up with, and I'm going to rewrite it for you up here, is p times 1 minus p divided by n. Okay. So I'm hoping that you can see, especially from this standard deviation formula, that as n increases, our spread is going to decrease, right? The larger the denominator of a fraction, the smaller the number, right? Now, the question that I get asked most about sampling distributions of proportions, it's like, well, if we can figure all of this out using a binomial variable, and we already have formulas for a binomial variable, why would you do that? Like, why bother, right? Because they're essentially talking about the same thing, right? Or you can describe the same distribution using both a binomial distribution, or you can describe the same variable using a binomial distribution or using a sampling distribution of proportions. It's just that the binomial variable counts the number of successes, and the distribution of p hat, the sampling distribution of p hat, counts the proportion of successes. But you're essentially describing the same variable. So, like I said, the question I get a lot is, well, why? Like, why do I need this? Like, why does it matter? And the short answer is sampling distributions of proportions are easier to deal with. Even though the formulas are a little bit more complicated, calculating the probabilities is much easier. And another really important reason that we need the sampling distribution of proportions is just because there are some scenarios that binomial won't work for, but the distribution of p hat will, right? If we just stopped at binomial, we wouldn't be able to expand further in our statistical studies. Okay, and that's essentially the reason why we deal with these things. Okay, so just as a quick review for you, the goal of all of this in dealing with these sampling distribution of proportions is we want to see essentially how accurate our sampling method is, to see how accurate our sample proportions are and how good they are at estimating or possibly even predicting the true population value, which is really what we want, right? Because remember, this class is all about a search for the truth, okay? So the last little bit of this video kind of essentially takes what we did here with the binomial variable, and I'm just going to give you the actual formulas now, okay? So what we saw in when we were talking about the binomial thing here is that the mean of a sampling distribution, so the true mean of a sampling distribution, which is noted with mu, and then the subscript is p hat. The subscript is important so that the AP readers know what kind of mean you're dealing with. Okay, but that should be equal to the population proportion, which is lowercase p, no hat. Okay, which again, we kind of have been talking about throughout this section, right? You saw that in this very fanciful graphic, right? Where we had the average, or the center of the sampling distribution, be equal to the true value, right? The parameter, right? The population proportion, right? Showing that it's an unbiased estimator. Okay, and then your standard deviation is this very fanciful formula with the square root. Okay, so standard deviation of p hat is the square root of p times 1 minus p over n. Okay, now you may be thinking to yourself, oh dear God, this seems like a lot of formulas to remember. Okay, lucky duck, all of these formulas are on the formula sheet that you get when you take the AP Stats exam. You do not have to memorize these formulas, but it's a good idea to know where they are on the formula sheet just in case you forget them. But honestly, you'll be using these a lot throughout the rest of the semester that at some point they'll kind of get ingrained into your brain, okay? And key thing to point out for sampling distributions of proportions, that inside the standard deviation, notice that I'm using P, lowercase p, the true population value, and not the sample value. Okay, that's important to note, and you'll see why when we get into the example problems, as well as when we get a little bit further into this semester, into Unit 7 specifically. Okay, right? Now, the only thing that's a little bit different about sampling distributions that haven't really occurred much in other distributions. I mean, we've had a couple of conditions that we have to check for binomial, but sampling distributions have conditions that you have to check. Okay. The reason that we have to check these conditions is so that we can tell if the sampling distribution is going to be approximately normal or symmetric. Okay, so these are your 3 conditions that you have to check. The first is the randomness condition. Okay, so the samples have to be pulled randomly from the population. Okay, so you have to have a simple random sample of the population. Okay, that's the first condition. Second condition, you're going to hear me call this the independence condition, or more often you'll hear me call it the 10% condition. Okay, which is you have to have independent samples, like it typically will be stated in the problem, or the sample can be no more than 10% of the population. Okay, typically the way that we do this is we take the sample size, multiply it by 10, and ask myself, is that less than the population size? Okay. And then the last condition that has to be met is something that you'll hear me call the success-fail condition, okay? Which is you have to have an appropriately large number of successes and an appropriately large number of failures, okay? So for proportions, the success-fail condition is NP has to be greater than or equal to 10, and n times 1 minus p oops, I'm over here struggling with my typing, must also be greater than or equal to 10. Okay. This right here, NP, is just your number of successes. Okay. N times 1 minus p is your number of failures. Okay, so the randomness condition kind of is self-explanatory. The independence or 10% condition, essentially what you're asking is my sample small enough? Okay, and then the success failure condition is asking, is my sample big enough? Right? Um, so the independence 10% condition kind of gives you like the cap, like the top cap of what your sample size can be, and your success failure is your low cap, right? Like it can't go below that. Okay, now the key thing about these conditions and the reason that we check them is because if we satisfy all of these conditions, then we can use all of the tools that we have for normal distributions. Okay, right? Because remember, what we're trying to check is, can the sampling distribution be approximately normal? Okay, so if these three conditions check out, then that means we can calculate probabilities using with our tools for normal distributions, like the z-scores, the z-table, um, the normal CDF on your calculator, right? Much easier than the binomial distribution, right? It's much simpler to calculate probabilities that way, all right? But if the conditions are not met, then we don't know that the sampling distribution is approximately normal. Okay. And at that point, you can't really go on with the problem, right? So you have to make sure that you check conditions first. All right, you guys. So that is it for the the basics, the formulas, and in the last video in this section, I'm going to show you some example problems with sampling distributions of proportions. So I'll see you guys in the next one. Bye, everybody.